than 2 years before D-Day, vast underground petrol storage tanks all over England were already linked by a pipeline network against the day when the invading armies would need the vital fluid to meet the tremendous demands of modern mechanized warfare. How could these vast stores of petrol be safely conveyed to the continent? It was Admiral Lord Louis Mountbatten who, as Chief of Combined Operations, asked, "Can you lay an oil pipeline across the channel?" After intensive research, the question was answered. And on August the 12th, 1944, the first PLUTO pipeline was laid from the Isle of Wight, soon to be conveying much-needed petrol to the invading forces in Normandy. As Mr. Churchill said, it was a wholly British achievement and a feat of amphibious engineering skill of which we may well be proud. Two distinct types of pipe were laid. The first, an ingenious adaptation of a submarine cable known as haze and laid by cable ships. And the second, a more revolutionary method, using steel pipe. Stewart's and Lloyd's are proud of their contribution to this great achievement, and this is their story of the production of the steel pipelines known as Hamel. Hamel is derived from the names of two experienced oil field engineers, H.A. Hammick and B.J. Ellis, who in April 1942 proposed a scheme involving the use of steel pipe. This resulted in a section of the Petroleum Division, later to be absorbed in the Petroleum Warfare Department, inviting S&L to cooperate with them in this most unusual development. A scheme had to be devised for laying a complete pipeline across the channel in a single night during the hours of darkness. Just think of the magnitude of this problem. High-speed laying was essential, so the pipe had to be joined before laying. Would it be possible to coil miles of pipe on a drum? A skeleton wheel, erected alongside the railway track at Corby, was used to try out what was obviously the most promising solution, provided the steel pipe could be coiled. Initial tests were made with lengths of 2-inch tube, welded together on the site and wound round the wheel, a locomotive acting as the source of power. At first, it was thought that a bending machine would be necessary to bend the pipe onto the drum and possibly to straighten the pipe leaving the drum. Tests, however, showed that it was unnecessary, both during coiling and uncoiling operations. The locomotive moves and the coiling of the pipe commences. Anxious moments, these. Will it continue to wind satisfactorily after its first complete lap? It does. The truck applies a tension of about 1 ton. Winding completed, the locomotive is now used to unwind the pipe. It moves off, and the steel pipe, which a moment before was wound round the drum, is paid out along the track. There were many experiments before the line was laid at this speed, and many trials before it was proved that tube of 3-inch bore could be as successfully wound as the 2-inch used in earlier experiments. But by untiring research, it was proved, and instructions were given to proceed with a scheme for the production of pipelines for full-scale trials. How were the pipes to be joined? On what type of drum were they to be wound? Experiments were made with a converted hopper barge, but by the time it was ready, more ambitious schemes were afoot, and her pipe-carrying capacity was too limited. Another start was made. This time a huge floating drum was built to pay out the pipeline as it traveled, carrying sufficient to span the channel. So was born HMS Conundrum, with a winding surface 40 feet in diameter, 60 feet between the flanges, carrying nearly 80 miles of pipeline. Nearly 80 miles of pipe. Meanwhile, a model drum had been devised to demonstrate the angle of flange most suitable for this work. Many were the knotty problems solved on this miniature drum. how to ensure the correct nesting of pipes when wound near the flange, the method of winding when starting a new layer, how to avoid a rise in the level of the coils. These problems were tackled, fought, and beaten on the small-scale drum. Further experiments with the model were made to investigate the action of water trapped between the coils and its effect on the loaded conundrum when towed. Research showed that the out-of-balance load due to the behavior of the trapped water would cause a heavy additional pull on the pipe during laying. Then, tests were made to simulate a winding with tubes slightly spaced, allowing the trapped water to escape. This resulted in greatly reducing the out-of-balance load, and in practice, this is how the lesson was applied. It is worth a passing thought that this pipeline is made from the same type tube as used in the Ingalls Bridge, where rigidity and weight-bearing qualities are essential. It seems rigid enough as the tank trundles across. Yet, this same type of tube was sufficiently flexible to be wound on a drum and then unwound like wire from a reel to be laid across the bed of the channel. In their large steel and tube works, Stewart's and Lloyd's experienced no difficulty in producing, amongst their many other wartime demands, the 1,000 miles of pipe required for this project. It was everyday work for these 30-foot lengths of steel bar to be broken into billets and fed into the furnace. And these men had not the slightest inkling that they were contributing to the success of a vast and ingenious undertaking. To them, it was just job 99, something urgently needed for the war effort. The production of this additional tube was in fact only a small part of the activities of the company, whose output of steel tubes during the war exceeded 275,000 miles, enough tube to encircle the globe 11 times. Now, the billet that was is elongated to a tube of some 30 feet. The ragged ends are sawn off and the tube enters a reducing mill, where again it is elongated to emerge a PLUTO tube of the required dimensions. From the cooling racks, the tubes are taken to be descaled and coated to prevent rust. No rust or scale must endanger the flow of petrol. Every tube must pass the grading test to ensure that only those of correct carbon content leave the mills. By this meter, any difference from standard is easily detected. Special plant and equipment had to be devised to make these tubes into pipelines up to 80 miles in length, and this was the method eventually decided upon. Lengths of tube from the Corby and Tollcross works were to be flash butt welded into lengths of 4,000 feet, nearly 3/4 of a mile, and then stored until required for winding on the conundrums. To the end of a length already wound would be welded a length from the storage rack. Winding and welding would continue until the required length was on the drum. A special site had to be found on which all the equipment for this project could be erected. It had to be one near deep water where the conundrum could be floated. The Tilbury dock area was chosen, and the trial factory known as A plant was built under the supervision of the Coombs Wood staff. It was a heartbreaking proposition. It is difficult to imagine that only a few months before, this was marshy wasteland, overgrown with shrubs and weeds. Even the existing roads and rail tracks to the docks were formidable obstacles when it came to carrying out the plan, and yet, within 5 months of starting work on the site, the plant was in production. The winding jetty, the South End welding shop, the 3/4 mile conveyor system, the North welding shop, and the tube storage. The first order placed was for 115 miles of 3-inch bore pipeline, and this plant was designed to handle that amount of tube. 7 production lines were laid out. The long lengths, while being produced, were conveyed to their full length of 3/4 of a mile on 7 parallel sets of rolls. At every stage, precautions were taken to ensure perfection. One failure in the underwater pipeline and the consequences would be disastrous. Experiments developed into successful tests across the Solent. The authorities were convinced and the order given to go ahead operationally. This meant an increase in the capacity of the trial factory, so B plant was built to run simultaneously with A plant, giving 14 production lines in all, 7 in each welding shop. At this time, the Thames estuary, far from being a safe area, was under constant enemy observation. And 6-inch crossover guide tubes were installed so that in emergency, they could be connected to the existing guide tubes and production or winding diverted to alternative conveyors. Wagons fully loaded with tubes arrived openly at the docks. No secrecy about the journey and no comment is caused. The monorail crane takes the tubes into storage. The wooden bungs, which protect the tube ends and keep out foreign matter, are removed before the tubes go to the welding shop. In the welding shop, the lengths are carried along conveyors to the inspection bench. Each of the 14 production lines is a complete unit in itself, consisting of a welding machine, 2 types of trimming machines, and a traverser. The inspector checks whether the tube has sustained damage during its journey from the mills. Satisfied with his examination, he applies a spot of paint and stamps the tube with his code letters. At the cleaning table, the protective coating is removed from the ends by spirit, the steel polished with emery cloth, and filed to leave a clean, smooth surface for the electric contacts of the welding machine. This shows the procedure for starting an entirely new 3/4 mile length of pipeline. A tube is pushed through and beyond the grips of the welding machine. A bung is inserted in the nose end and the pipeline's identification number painted near the end of the tube. By hand, the nose end is moved forward into the trimming machine while the open end is positioned in the welding machine. The latch plate is dropped to prevent any forward movement of this tube when the internal flash removal tool is sent forward through its entire length. It is fitted with cutters to remove the obstructing metal, holes through which air is forced to cool the weld, and brushes to clean the bore. As the tubes are welded, a flash or flange of metal and the spattered metal from the welding is left inside, which, if not removed, might cause obstruction. The problem of how to remove this called for extensive experiments before this tool head was developed. The tool head emerges, proving the bore to be clear, and the latch plate is lifted, allowing the tool head, now carrying the tube forward, to enter the tube into the welding machine. The tool head is now beyond the welding position, so that the dust and swarf removed by the cutters may be drawn out when the ends are welded. If the tool head were to be passed through after welding, the dust and bits of metal would be pushed forward into the longer length of pipeline. The weld commences. It should be noted that an inspector must be present during the entire operation. Notice how the pointer indicates that the right-hand head is creeping forward. When the flash cuts out, it will dart forward, forging the weld. As the weld cools, charts are checked for consistent flash current. With welding and cooling completed, the flash remover is brought into use, and this cutaway section shows clearly what is happening. The shaft is rotated and the cutters brought back to remove the flash left inside after welding. After cutting and brushing small bits of metal from inside the weld, the tool head is withdrawn, sweeping clean the length of the bore. And the machine is reset for the next weld. The nose end is hand-fed into the traversing machine, which grips the tube and carries it forward. The next operation is to trim the flash, which is also left on the outside of the weld. As the tube leaves the trimming machine, the inspector makes sure that the cutters have not cut into the wall of the tube. If they have, the weld would be cut out and the tube ends re-welded. The whole success of this great undertaking depends on perfect welding. As well as routine tests at Tilbury, laboratory tests and examinations under the microscope were carried out at Corby on weld specimens sent from the production lines. Sections cut from the tube wall underwent the repeated bend test, quality being checked by a comparison of the number of reversals required to break the weld with those required to break the parent metal. Meanwhile, in the welding shop, the traversing machine propels the pipe away from the building inside one of the 7 guide tubes, emerging onto the conveyor system 250 feet away. Outside the building, the 7 guide pipes converge and line up with the stepped conveyor. For halfway down the conveyor system, the pipe noses along on its own. But at the point where the system changes direction, a linesman keeps a watchful eye to see that it maintains the right course. This system of conveying the welded length into store avoids any interruption to the flow of war traffic passing overhead, the drivers blissfully unaware that the slowly moving pipeline below them will soon feature as Operation PLUTO. About 1,000 feet from the end, the system veers to the right, and the linesman steers the nose end on its course round the bend. A message is sent to the welding shop when the pipeline only needs another 25 feet to complete the run. The charge hand indicates the position to which the last made weld must be traversed to give the required 25 feet of movement to take the nose end just beyond the far limit of the conveyor system. At the north end, the oxyacetylene gas burner cuts through the pipe, and the 3/4 mile run of pipeline is ready for storage. Thrown off by hand, its own weight and elasticity offloads the pipe at the rate of 120 miles an hour, 14 tons shifted by a single movement of the hand. Very different from the early A plant days, when the pipeline had a playful habit of leaping across the conveyor and dropping into the wrong storage pen. Time wasted in pinching it back into its correct pen when there was no time to waste. But this gadget was devised, trouble ceased, and time, the all-important, was saved. and B-plant conveyor was an even greater improvement. The moment the offloading is completed, a bung is inserted in the nose end of the new pipeline. And the welding shop is signaled to carry on. Nothing is left to chance. Preparations are now made to blow out the newly offloaded pipeline. Although the inside of each weld was smoothed and brushed out, just to be quite sure that the inside of the 3/4 mile length is perfectly clear, compressed air is forced through the pipe and any dust and swarf is blown through and deposited in the bucket. The bucket is left in position, and at the far end, the inspector inserts a hollow steel bullet. The air hose is coupled up again, and the bullet is blown through the entire length, attaining a speed of 100 miles per hour. The most stringent tests that engineering skill and ingenuity can devise are constantly applied. As soon as the no obstruction test is complete, the open ends are sealed. A plate is welded on at each end. A white line painted round the pipe and the pipeline cipher number added. From the store, the pipelines are loaded onto the winding tracks. The linesmen seem to have little to do, but they are an insurance against any possible trouble. Notice the extreme flexibility, yet this tube is precisely the same as that used to make the Ingalls Bridge, which carries weights up to 70 tons. While the miles of pipeline were piling up in the storage pens, the Petroleum Warfare Department had arranged the construction of further conundrums. When launched, the driving chains are fitted to the teeth round the flange of the drum. At the start of a new wind, the initial rigging is the work of the Royal Navy, who attach the buoy. This rigging plays a very important part at the end of the pipe laying, for as the end leaves the drum, the buoy will be snatched out and mark the end of the lay near the coast. A rope is attached to the buoy, which is secured to the end of the pipe and will be used for hauling the pipeline to the shore. The buoy is dropped into the recess and secured by slats. And here is the same buoy as it floats to mark the end of the lay. Stewards and Lloyds wish at this point to pay a generous tribute to those of His Majesty's Navy who gave their unstinted cooperation in this most unusual project. Before the wind proper commences, notice how the slats are inserted in the grooves. One snatch of the rope and the buoy is free. Rigging completed, S&L again take over. drum rotates to take the strain and the wind commences. Passing through the welding shop, the tube is examined to see that no damage has been sustained while lying in store. Through the snubber, which applies tension, up and along the catenary, and into the cab, which is the control center for winding. The power which turns the drum and draws the pipe forward is controlled from the motor house. As the nose end of the pipe reaches the window in the flange, a socket, plug and fin plate are welded on and nest inside the window. This is needed for an important final leak-proof test when the drum is completely wound. As the winding continues, preparations are made to draw forward the next pipeline into the welding shop. As the nose end reaches the cutting machine, the pipe is pushed over to form a bow between the entrance to the shop and the cutter. While the pipe being wound is still passing through the shop, the cutting machine is positioned to remove the sealed end of the pipe to be welded, which is clamped in the vice jaws. With the sealed end removed, the cutter is withdrawn and the end is cleaned in readiness for welding. As the tail end of the moving pipe approaches, contact is made on the intercom.
Welding shop to cabin snubber. End of line approaching. Stand by for stop signal.
The stop signal, heard by all stations, is given when the end reaches the welding machine. The tail end receives the same treatment as the nose end when it is positioned in the cutter. Tail end removed, cutting machine away, and thoroughly cleaned. The pipe being wound is carried across to be clamped in the left-hand grips of the welding machine. An awkward job, and one needing the assistance of men outside the shop to straighten up the pipeline before the grip can be correctly clamped down. The new pipe, still pulled by the winch, is guided into its place in the right-hand grip. Before clamping down, a sandglass test is made to check the timing of the weld. Controls are switched off and adjustments made to position the pipe in the grips. The bend in the rear being ample to allow the pipe and the moving head to surge forward at the moment of upset. The weld commences. After welding, it is not possible to remove the internal flash of metal. However, as this only occurs at 3/4 mile intervals, any resistance caused by this slight fin of metal is negligible. The pipeline is swung over to the winding line, and another 3/4 mile length is ready for the drum. The bow in the pipeline is straightened up and the pipe is drawn forward into the snubber where brake gear is applied to retard the forward movement as it is wound onto the drum, keeping the pipe between the snubber and the drum in tension with a pull of 2 to 5 tons. It is fitted with caterpillar tracks similar to those on the traverser, but instead of driving, these retard the pipeline as it journeys through the snubber, out of the snubber shop, up the catenary, through the cab, and so onto the drum. The cab, from a control inside, is moved at will by means of a chain, so keeping the pipe in proper alignment for the coil being wound. Wooden blocks are fitted near the flange to ensure correct nesting of the pipe. As the drum restarts, the turns are close packed with a mallet, the clips preventing the coils from touching and entrapping the water. The full-length wind takes 3 or 4 days to complete, and tidal problems have to be considered. At the end of a day's wind, tensioning gear is put into operation to take care of the considerable rise and fall of the drum due to variations in the depth of water in the dock. This keeps the last few coils tight on the drum while allowing enough play to avoid undue tension on the pipeline. The following morning, the process is reversed and the load of weights lowered to its normal position on the block. The wind continues until the tail end of the last pipeline reaches the welding shop. A pressure gauge is fitted to the tail end and an extension pipe fitted in the nose end. Carbon dioxide, soluble in petrol or water, is forced into the pipe to expel the air, and both ends are closed for 24 hours. Chart readings are taken during this period to ensure that pressure is maintained, which proves that there is no leakage in the 80 miles of pipeline. The nose end of the pipe that will start the next wind is pushed forward and shackled to the tail end of the wound pipe. Once more, the drum revolves, carrying the last 400 feet to the cab, where the tail end is shackled, leaving the nose end to await the next conundrum. The rope is now fixed to the tail end of the wound pipe, which will be fastened to an anchor on the sea bed to pull off the pipe and start the lay. For the last time, the drum rotates to take up the rope and complete the winding on HMS Conundrum, a vast floating bobbin weighing 1,600 tons when fully loaded, the weight of a destroyer, and presenting a towing problem greater than that of the Queen Mary. Now the Navy takes over. The drum is finished and ready for sailing. In September 1944, the first Conundrum sailed to make its contribution to the PLUTO scheme, which guaranteed a delivery to the continent of millions of gallons of petrol without harbors, docks, or ships. On the invasion coast, the liberating forces were ready to receive this vital artery. Pipes and Victolic couplings were there in plenty. Royal Engineers had been rehearsed and trained to lift, carry, and couple those pipes blindfold. All this tied up with those innocent-looking bed and breakfast apartments on the south coast of England. In reality, pumping stations to be connected at a moment's notice to the vital Channel pipelines. Just imagine the day, little more than 2 years after the birth of the idea, when the pumps started to work and petrol flowed from England to points in France, Belgium, and eventually into the very heart of Germany, without which the thousands of tanks, trucks, and mobile machines of modern war would have been paralyzed and useless. So the 1,000-mile system of pipeline in England was extended to form a lifeline to the Allied forces, until no less than 20 lines were laid from the Isle of Wight and Dungeness to Cherbourg and Boulogne. Such was the miracle of Operation PLUTO.